Well, I hope you all are refreshed from spring break, or at least as much as you can. Again, still 9 in the morning. No amount of week off can undo 9 o'clock on a Monday morning. So we are at the point where I sent in your articles to Daniel Nenny at Dr. Nenny at SemiWiki. He thought they were very good. I was very impressed with the final drafts. Y'all did a very good job of taking my edits and incorporating them. And I posted your grades on that. Most of you, it was out of 200, so you guys did very well on that. So then it's just a matter of him getting them up, and then there should be feedback you get from posters. And that last week of the semesters, you guys will be just presenting on discussing your article. And I know you can get up here, and you guys get to be on this machine and see how that is. But they're very good, and I got the Verilog submissions through the email, and you guys got my email that I sent out with the due dates for the labs so all the files you'll need to complete those are up. So for those of you who are go-getters, I'm sure some of you have already tried looking at them. Every file you will need is on there. The one thing, there is one WinSpice, which is a 28-day free trial. You only need it for 7, so good, you don't have to pay. And so I think you only need it for lab 1. My recommendation is try to figure out how to pace doing it. It doesn't take too long, but the only time it takes long is if you somehow put it off to the last minute, then it magically gets longer, as all labs tend to do. So my recommendation is try to pace it a little bit. You shouldn't be taking more than 6 to 8 hours total, including writing it up. For those of you who haven't had me before on labs and submissions, I have a section where I ask you to describe the challenges you had on it. So if you get to the point where the labs are designed where if you get stuck, that's okay, because there's a completely different part. So if the first part is design an inverter, then you design a 2-input NAND gate in CMOS using their Lambda-based design rules. If for some reason it's not cooperating and you can't get it to work quite right, that's okay, because the next step does not depend on it at all. So you just describe why it was, what it was about it that was really messing with you, and just as long as you document it thoroughly. Don't try to I wasn't born yesterday, I know, when students are trying to slack and don't do something like oh, it didn't work, the end. If you show me that you put in effort, I will reward it. So when in doubt, document. So today we're going to start going into combinational circuit design. So the general idea is that up to this point, we've had this C in CMOS as complement. So we've had a PMOS pull up and an NMOS pull down. And we've had this ratio, typically 2-to-1, because of the fact that, why do we have 2-to-1 ratio of PMOS to NMOS? What's the justification? Yeah, what is it about what's the underlying physical principle that forces us to have a PMOS twice as big as an NMOS?
Because the NMOS is just a P active with one single NMOS, and then the PMOS has the NMOS with.
That's not quite right. You do have correctly described the design of them, but what is it about the PMOS has to be, the width of the PMOS has to be twice the size of the width of the NMOS?
Because PMOS has more electrons?
Not more electrons.
So it carries more.
No. You're on the right track. That's something. The word electrons is in the right answer. Welcome back from spring break. I'm giving you a brain teaser. So you just can remember lecture 1. It's because the mobility of electrons is twice that of the mobility of holes, right? And we went through that whole problem, we went through a proof, and we demonstrated that. And as a result, you have to make the PMOS transistor twice as wide. So as a result, we have these PMOS and NMOS transistors where if we were to design, remember this would be 4, and this would be 2. We have our inputs here. So that would be 2. So basically the PMOS and the NMOS is 4 and 2. So the whole idea is now we're going to have to deal with performance and area constraints. Because up to this point, PMOS has really good noise margins. They're fast. They consume relatively low power. They're relatively insensitive to device variations, which you'll learn about in section 6. And they're easy to design. So you can use stick diagrams and other CAD tools, which you'll do in the 3 labs. And they got widely supported by CAD tools. So if you recall, here's a sentence from section 3. Logical effort tells us that NANDs are better than NORs and that gates with fewer inputs are better than gates with many. So why were NAND gates considered better than NOR gates? So remember this logical effort statement here? This logical effort tells us that NANDs are better than NORs and that gates with fewer inputs are better than gates with many. So this first part, NANDs are better than NORs. Why is that? It has to do with the question, just the last question I asked you as well. Try to combine some concepts here. Come on, guys, spring break's over. No, they have the same number of transistors, but what about it? You're on the right path. Yeah. So what does that mean, though? Okay, so you are correct. The answer is this is due to the fact that we require 2 lambda PMOS compared to an NMOS for an inverter. And then it goes back to the electrons have approximately twice the mobility of holes. So how does that tie in to the design of a NOR gate as opposed to a NAND gate? So if I were to ask somebody to go up to the blackboard over there and draw me a NAND gate and a NOR gate using PMOS and NMOS, who could do it? Really? This is the way? Come on, guys. Come on. No one's going to volunteer? Literally, no one's going to volunteer. No, hold on. Hey, no. This is not the way this is going to go. Hey, come on. What's going on? I'm asking easy questions here. Why was a NAND gate considered a better design than a NOR gate? If I don't get an answer from somebody, I'm going to give this question as a pop quiz. Somebody answer the question, please. Or at least try. There you go. Now you guys are starting. There we go. So think through this process. So Josh and Trey. So as you guys are writing this out, what are you guys thinking?
Well, first, just draw the truth table.
Okay. So you're drawing the truth table. So what about the NAND gate and NOR gate truth table is unique?
For NAND, everything is 1 except the last one, which is 1.
Right, and that becomes a 0. So what about the pull-up? So then you design your truth tables for NAND and NOR. So what's the next thing you're going to do? You're going to design the pull-up network, right?
Well, I mean, like, I guess just looking at, the only difference is just add inverter to one to get the other. Right? Or
No, that's not right. No, and is NOR.
Yeah.
I mean, it's and NOR, but okay. So the reason. Okay, so if you were drawing out, right? So if you were drawing out, so you have your truth table, and this is a NAND gate, right? Look familiar? Then your NOR gate. Looks like that, right?
Effective capacitance.
There you go. Gemma's starting to speak.
Effective capacitance for the NAND is much better because you have those two, and it's only effective output capacitance with just one compared to the normal.
Right. So if we were going to effective capacitance and doing our RC comparisons, right? You have 2, and these would be 2, right? And so you have to add 2 times the number in series. So this becomes 4 and 4, and this becomes 1 and 1. So as a result, the effective capacitance of your NAND gate is better. It's also smaller, right? All right, so did I just close the PDF out entirely there? I guess I did. Okay, so as a result, the whole point is that you see that these NMOS transistors are typically smaller than PMOS and accomplish the same amount of current and the same effective capacitance, right? So as a result, and the reason why I wanted you guys to try to struggle with this a little bit is some designers said, okay, well, let's see if we can actually design circuits using just NMOS or as few PMOSs as possible. And so we're going to go into what they tried to do and how they struggled with that. So what we were alluding to is this difference in 5.1 here, where define and differentiate between static and dynamic CMOS. So static CMOS is the conventional CMOS family, where there exists at all times some mechanism to drive the input either high or low. So that's what we've covered up to this point, right? We have covered this static CMOS. Whereas dynamic CMOS, there's going to be different sizes, and we're going to exploit temporary storage of information in stray gate capacitances to drive the output. And so in 5.2, it's kind of a review of a concept we went over earlier, but we have not A or not B is equal to not AB, right? And then you have not A and not B is equal to A or B not. The reason why, if you have this here, you have a NAND gate, which is an inverter, after an, I would say, if you have an AND gate, which has an inverter, so that's 4 plus 2 is 6, right? And then you have this inverter and this inverter as well, so this is 2 and 2. So that becomes 10 transistors. But the NOR gate here is only 4. Same thing, you're going to get this will be 10 transistors and this is 4 here. So anytime you can use this concept of bubble pushing, which is basically just utilizing De Morgan's law, you can actually significantly reduce the design of the circuit using the exact same logic. So we can actually use this to actually reduce the size of our circuit, and especially since we're going to be trying to get to these NAND gates, ideally we get this kind of situation down to here. So we can make, and the thing is NAND gates are functionally complete. So you can create an entire circuit using NAND and NOR gates. Because you got the 1, 1, 1, and 0, right? And then 1, 0, 0. Sorry, NAND and NOR. So it's, yeah. All right, so this example here is a really good combining concepts type question, this 5.1 here, because we have AB and CD, so it's not inverted, right? Using bubble pushing. So we're going to take an actual logic, because up to this point, everything's been F equals not AB, right? And the reason why is because that's attempted to reduce the complexity of the problem. So now we have this problem here, and we're going to try to actually reduce it. So here it's AB or CD, right? So that's our initial logic function. So the first thing we're going to do before we do anything is we got to go to our design constraint. Using NAND, NOR, and NOT gates. So we have to bubble push, right? So the first thing you want to do is you can take the AND gates and turn them into NAND gates and then just put an inverter on those, right? And then the same thing with OR gate. You can take an OR gate and turn that into a NOR gate and an inverter. So now what's going to happen is you have two NAND gates and you use NOR gates with these bubbles, right? So if we know that the NOR gate is the smallest one, we can actually just get rid of this bubble here, and we turned it into this OR gate with two bad inputs, right? Well, this went with two negated inputs, sorry. So two negated inputs, that actually just is equivalent to NAND gate. So the goal should be to try to make this circuit as small as possible, and this is the smallest possible circuit. So there's a different way you could actually do this. You can start here, and you can go here, except you can leave this off and just kind of break it down into pieces. And if you push the bubbles, this actually becomes NAND, NAND, and they both go into just the OR gate. And then you just use De Morgan's law there to convert this to a NAND gate.
So every one of these circuits is the same thing?
Yeah, these are all four of these are logically equivalent circuits. So this is the stages of bubble pushing. So you can see I actually got rid of this here and just push those there to reduce the complexity of the answer.
Could you have done that by doing De Morgan's on just a formula A and B or C and D?
Yeah, I mean this is just a circuit equivalent of doing that. That's a very good question. So yeah, so if you just did the De Morgan's on that, so that becomes, you know, if you made not A or not B and that like that, so you're inverting it on the output here. And well, if you're doing that, then that's breaking down this way, and that eventually becomes like that. Okay, so that's the first part of the question. So everything else, now we're going to figure out our delay. So each input can present a maximum of 20 lambda of transistor width. The output must drive a load equivalent to 100 lambda of transistor width. So we've done our calculations and we figured out that the output is 100 lambda. So now we're using a CMOS pull up and pull down network. We're gonna calculate the path efforts. So the path electrical effort, as you recall, is going to be the output divided by the input, which is 100 lambda over 20 lambda, so that becomes 5. So we have no branching in this circuit, means we don't have anything going off this way or this way, right? So the result branching is going to be equal to 1. So we have each path goes through 2 NAND gates, right? So if we recall, it's n plus 2 over 3. The number of inputs is 2. So it becomes 4/3 times 4/3 equals 16/9. And our parasitic, remember the parasitic delay of each NAND gate is 2, right? Or with the 2 inputs. So if it's 3 inputs, it's 3, and so on, if you recall from that TGO. So the path is 2 plus 2, which is equal to 4. So then we're going to calculate our path effort, and then we have our 16 divided by 9 times 5, and then our branching is going to be 1. Multiply those together and you get 80 over 9. Does that make sense so far? All right, so eventually we're going to get into how we calculated all this, the rest of this stuff out. But let's just bear this in mind. So remember, 6 over 3, right? So if we're calculating the whole circuit here, we have, remember, it's AB plus CD, n plus 2 over 3. So that becomes 4 plus 2 is 6. And then if we want to do the circuit, we're going to multiply it by 3 over 3 to get the inverter, right? So we get 6 over 3. And then same thing, we just multiply 6/3 times 5 times 1 is 10. And so what we've actually done here is we have designed a pull-up and pull-down network for this. So we had A, B, or C, D. So we used our design rules that we came up with earlier, and we had A, remember, and they're in parallel, right? So this was B. And then normally we draw it C and D. They didn't have any space there, but it's the same thing. So then when they're in parallel, so this is out. So then A and B are over here. And then C and D are over here. And so, if you recall, each path, it's 2 times the path you go through. So if we had to go through B and D, it becomes 4 and 4. So each of these are 4. So this is going to be 2 and 2. And that's where the 6 comes from. And so for right now, this parasitic delay of 12/3, just I believe button for right now. We haven't gotten there yet, so just I believe, just press it and roll with it. So we've calculated 80 over 9 and 10 here. So, and I made it, I should say, if you've ever seen this AOI 22 gate, that's what we just designed here. So, and an inverter. So we put an inverter here. So we put a PMOS circuit there. And then MOS here. And then we'd have our full design, right? And we accounted for that by putting in that 3 over 3 there. So now we have 2 different designs. We have 8, 10, and we have 4, 8, and 12. So this is 12 transistors, and this is 10 transistors over here. And so next thing we want to do is we want to compare for our delay. And so we use our equation for the number of gates times the times the effort plus the parasitic delay. So for the NAND-based circuit, it's 2 times 80 over 9 to the 1/3. That should be 1/3, not 1/2. The numbers are right, but the typos. And here we had a delay of 4, which we calculated to be because of the 2 NAND gates, right? And so we had 12/3 plus 3 over 3. 3 over 3 comes from the inverter we have to end here. And so it became 15 over 3, which is 5. So our delay becomes 2 times 10, which we got here, plus 5, which is 11.31. And in this case, our best stage effort is here it's 80 over 9 over 1/2 because there's 2 gates, same thing, 10 over to the 1/2, which is 2.98 and 3.16 respectively. And so for our input capacitance, we're just going to do the same thing. We have our, your output times the output capacitance divided by our best stage efforts. So it's 4 over 3, right? For NAND gate. And AOI is 1. So it becomes 100 times 1 over 3.16, and 100 times 4/3 divided by 2.98. So the input capacitance has to be 44.74. And so I say use 44 because you're actually going to design your circuits based off of these whole numbers. So in this case, this one became 31.64. So use 31. And so how does that actually work? Okay, well, here are the final circuits using those numbers. So here we have 44, right? And here's 31. So that's approximately 90%. So how do we calculate that? So remember we have this, the ratio is going to be, it's 2 and 2, 2 and 2 there, right? So these should approximately be, equal to 44. So you can look at those and go, okay, well, if I want those ratios to remain the same and have them add up to 44, well then that's just 22, 22, 22, and 22, right? Same thing here. It's approximately 2 to 1 for an inverter, right? So it should be 31. So that's approximately going to be, so if I had 31 equals 2x plus 1x, right? So going back to algebra, so 31 divided by 3 equals x. So that's approximately equal to 10. So then this just becomes 10 and 20. And so how do we want these numbers to be rational numbers? We want them to be whole numbers. So then so that if we did this was 20.67 and 10.33, right? So then we just round and this becomes 21 and that becomes 10. Same thing if you remember from, I'm going to scroll back up to the beginning of it, right? So remember we had 20 as the input, right? Maximum lambda of 20 width. So what we're going to do here is, going by the same logic, these add up to 20, right? 10 and 10. And here it's the same thing, got 13 and 7. So that's 20, and then we use 44. I'm sorry, both of these are 20, and this is 44, this is 31.
Do you always round down to get the capacitance?
Round down? No. Yes. Oh, you're talking about here? Yes. Just because you remember, if the simple answer is remember the capacitance is the ability of a circuit to hold a charge, and in this case we're attempting to measure how fast we can propagate it through the circuit. So the capacitance is the retarding ability in that case. So anytime you can round down a little bit, you want to do that. To answer your question. Good. So basically what we did here is given our knowledge of logical effort and path effort and best stage effort, we were able to calculate what the input capacitance should be based on two different designs of a circuit. So these two circuits are logically identical. So here we have 40, 40, and this is 88, right? So here this is 31, and that's 80. This is 88 plus 80. So this circuit is much larger than that circuit. So this is an example of. So ultimately, why is this a good question? So I mentioned that this is a good question. I'm going to scroll up here for a second. Okay, so basically we have some sort of logic, right, that we're trying to calculate, and we have input and output transistor widths, and the team comes to you and says, "Give me a good circuit." So we are designing a bunch of different circuits. So this is obviously this would be a bad design, right? So we use bubble pushing. We try to get down here so we can use the CAD tool. So if you're using the CAD tool, it's going to give you this, right? And if you're having different levels of abstraction, you get AB not, CD not, and these are ANDed together. And especially if you're doing it at Verilog level, that's what you're going to end up getting. If you use a SPICE tool, if you use the algorithm that I presented earlier in the semester, you're going to get this, right? You'd get this circuit. And then you have to put an inverter on the end, right? So now you have to, using what this pathological effort and your logical effort, justify which circuit you'd want to use and why. So if your constraint is area, you definitely want to go with the AOI 22 gate. If you recall from earlier, I kind of alluded to it by saying various circuit here. This various circuit try to reduce the capacitive effect of NMOS while trying to reduce the area. Performance or area constraints occasionally dictate the need for other circuit families. So your bossa comes in, give me A, B, or C, and D, and I need it to be as small as possible given these input and output capacitances. So this is the smallest possible circuit here. So different design techniques for different constraints. If you want it to be fast, if high performance is your requirement, well, if we go back to delay, the NAND-based circuit is 9.66 and the AOI 22 is 11.31, right? So which one is faster? It's the NAND gate. Because of the way that it flows through your circuit, right? As opposed to see how this can be more complex. If I'm B, well, I gotta pull out this way, right? So this is larger, but it's less complex in terms of capacitance. Especially for those of you who did your semi-wiki articles, on end of roadmap transistor design or single electron transistors. The smaller and smaller they get, the more issues you have, right? So this is a good example of that. So if those of you had 385, I harped often on this concept of good design requires good compromise. This is a quintessential example. Computer engineering, electrical engineering. This is if you really want to, obviously I don't know what your career aspirations are. Since I'm teaching digital CMOS, my goal is to try to put you in the best possible position to get a good CMOS job if you so desire. But even if you don't do CMOS and you're like, oh, I'm never going to touch a CMOS circuit in my life, screw this, I hated it. I hated NMOS and PMOS and mobility of electrons, and I just, grr. This type of problem is really good to understand anyway, because it's important to understand how to present, different. In computer engineering and electrical engineering, there's never just going to be one solution. And the person that you're making your circuit for is going to demand more than, is going to have a specific set of demands. If I want it small, then you got to figure out which one's going to be the smallest design. If I want it fast, that's going to be your other design, right? So being able to work through this kind of problem and the thinking process behind this kind of problem is going to be valuable to you no matter what you end up doing. So since I went on a rant about it, you probably know what that means, right? Expect something like this on the take home. But does that make sense? I promise it's not just me droning on about, nanometer size transistors. Okay, does anybody have any questions about what we did in this problem before I move on? All right. So at this point, now we're going to try to push the bounds of this. What can we get trade-offs, and how is this going to bite us in the butt somehow? So 5.3, just this is this concept of asymmetric gates. So what we've designed up to now is we want symmetric gates because we want all of our inputs and outputs to be identical or close to it as possible, right? But sometimes if you're really trying to push the boundaries of size, or you're really trying to push the boundaries of performance, sometimes you're going to tingle with circuits, and then sometimes you're going to come up with these different designs. So asymmetric gates inherently favor one input over another because one input sees less capacitance than another. And so this 5.2 here is a good description of why this is, and we're going to see why it favors one of the inputs over the other. So does it favor input A or B? So 5.2, describe the following output transition occurring when one input held at a stable 1 value and the other rises from a 0 to a 1. So here we have two different scenarios. We have one where A is 1 and B is 0 to 1. And we have the other one where B is held at 1 and A goes from 0 to 1. Right? Which input does the circuit favor? Your answer should describe both input A rising last and B rising last. So next, redesign the circuit to be symmetrical and prove it's symmetrical. So here's our comparison. So if input A rises last, so in this case we have B is 1 and A is 0 to 1. Right? Node X, so that's this node here. Node X has a 1 on it, right? So when it's a PMOS transistor, that's already off. I'm sorry, it's already on. Sorry. Right, so we try to turn them on. 1, 1 puts a 0 on the output. So our PMOS transistor for B is already at 0 volts. We've already created an inversion region and we're here. So node X will be at 0 and it was discharged through the input B transistor. So no charge is going to be delivered to this node. So therefore when A goes from 0 to 1, therefore you just discharge on this transistor, so it's going to be 6 RC. So this is 6 here, that outcoupled capacitance is 6, so it'll just be 6 RC. Ignore this equals 2. I didn't include the RC number, so the solution is possible to solve it without it anyway, because it's comparison of 6 RC and it's going to be 7 RC for the other one, I think. So in the second part, we're going to be using our summation, right? So from our RC design. So for input B rises, that means A is 1. It means A is on, but B is off, right? So we have to discharge both capacitances. So remember we have our T model, right? Our pi model. So it's cut in half. So that's where the R over 2 comes from. Over 2C, so that we have half of this times the capacitance, plus, and then we sum R plus 6C, right? So this becomes 7 RC. So as a result, since our Elmore delay is 7 RC for the B input rising, and it's just 6 RC for the A input rising, this means that our input favors A. Does that make sense? Okay. Remember our pi model? Yeah, so if we had our pi model, we had R over 2 over here, right? So then we multiplied that, and then we had the capacitance. Yeah, so we had the R over 2 times the capacitance, and then we had that other value there, right? So that's our pi model, or P model, so we also called it. So R over 2, but then we sum the resistances and then multiply it by the next capacitance, right? So we had R over 2 and R over 2, which we also can take from, so these are 2R over 2 divided by 2 becomes R over 2, right? And then this was R over 2 plus R over 2, which becomes R. And then R is multiplied by 6C. Okay, good. So the last part of the problem is we've compared A and B, and we determined the Elmore delay. And so the last one is, how do we make it symmetrical? So what we're going to do here is we're actually going to do something called split rail. So what we're going to do is, instead of 2 and 2 here, where the reason why the circuit favors A over B, right, is because when A is switching, this B transistor is already on. So what we're going to do is we're going to split these in half. And we're actually going to make this 1 and 1, where the A input is here and the B input's here. And then we're going to have a second rail where this is the B input and this is the A input. So we've cut it in half and we've accomplished the same resistance. We don't touch the pull-up network in this case. And as a result, in this first one, in this first case here, so this one, A rises last, so in this case, this one's activated already and this one's activated already, right? So this is the case, the one on the right, we had that case initially. I'm sorry, the one on the left, we had that case initially, but we've split it up here to mitigate the effect. So then, therefore, and this is the statement I've included, therefore, no matter which input rises last, the circuit will rise equally. Okay, so in this case, now we're going to be trying to take advantage of these skews, right? So skewed gate inherently favors one edge over the other. So eventually we're going to get to this concept of clock skew. But high skew tends to favor the rising output transition, and low skew tends to favor the falling output transition. So what that means is, which one is faster in terms of low to high or high to low? So in this particular case, if you think about a NAND gate, right? So if we had, so let's think about an inverter. Let's think about an inverter in the case of PMOS and NMOS. And let's say for some reason instead of doing this 2-to-1, we just did a 1-to-1. Well, what's going to happen is, because the mobility of the holes is slower, and everything relates back to this logical effort, Elmore delay. We need this capacitance in order to improve the speed, right? We need to improve the width in order to account for the hole mobility. So what's going to end up happening is, a circuit where this is actually just 1 is going to favor the instance where it goes from 1 to 0, because this switch will happen so much significantly faster. So in that case, would be a low skew gate. Whereas with the high skew gate, that would happen if we somehow had like a 4 and a 1 there. That would make the rise significantly better than the fall. So you see the difference? That would be what a high skew gate looks like. In an ideal situation, if you are so permitted by your customer, you want those to be essentially identical. And when I say essentially identical, when you start getting into the fourth decimal point in a nanosecond, if you have 12 nanoseconds and it's 11.9996, at that point it's essentially negligible. I've made that mistake and tried to, God, they're so close. Why can't I figure it out? And it's at some point you just deal with quantum levels and there's nothing you can do about it. So I have a set of high and low skew. So I mentioned this was a low skew gate, right? Here, that's the circuit that we designed. You see how the transistor is reducing, right? Here, same thing. High skew is if the example they gave is 2 to 1/2. The example I gave was 4 to 1, right? Same thing. So the whole goal here is taking advantage of those electron mobilities, and that's why I was kind of hammering you guys to try to jog your memories at the beginning of the lecture, because all of this involves how you design circuits. So remember, this is normally 2 and 2, and this would normally be 2 and 2. These are the circuits that meet the design constraints that we said at the beginning, right? So anytime you kind of mess with those numbers, what ends up happening is you mess with the capacitance, which messes with your pathological effort. So the path effort is the ability to meet those timing constraints. So these circuits are unskewed, meaning we have designed them specifically to ensure that the rise and fall times are the same. And if you look at this high skew and low skew, our high skew favors 0 to 1 because of the ratios are off in favor of the PMOS transistor, and the low skew are the ratios in favor of the NMOS transistor. So if I were a designer and I was trying to push you even harder on lower area, which design would you go for? Low skew. Very good. So here we have the PMOS transistors in the unskewed gate are, their word, enormous, nor provide equal rise delay. They're relatively larger, right? So therefore, by accepting a slower rise delay, the PMOS transistors can be downsized to reduce input capacitance and average delay significantly. So this statement, that's kind of the math that you did in your head. And so these are, this TGO 5.6, are your fastest PN ratios. So how can you make it, these are the fastest possible circuits right here. So this 1.414, what is that number approximately? No, more specifically, what 1.414? Think back to math. That's a
pi over 2.
Not quite. 414 pi over 2 is approximately let's see, with 1.7 is 3.4, so 1.6 is 3. Yeah, that's not quite right. This would be 2.8. Yeah, there you go. That's what I was looking for. It's the square root of 2. So they found square root of 2 over 1. Then they have their up, down, and average efforts. So for NAND and NOR, it happened to work out where instead of these being, this would be 2 and 2 here, and this would be 2 and 1 there for NOR. So they yeah, they're basically the n-skewed ones, yeah. So what ends up happening here is this reducing the PMOS from 2 to the square root of 2. If we did the calculation, it's actually an improvement in delay of about 3%. So it's not really that much. However, it significantly reduces the transistor area. So it goes from 2 to 1.414. So that's 2 over root 2, which is actually, we've reduced it by the square root of 2. So the benefit is, by reducing the area, we're reducing the input capacitance. And if we recall that power consumption is CL VDD squared times the frequency, right? So if we're reducing this by the factor of square root of 2, then what we've actually done is we've reduced the power consumption by the square root of 2. So your trade-off is I'm getting this really good reduction in power consumption, but as a result, my input and output delays are not the same. So therefore, when you have timings, you remember in 385 and in microprocessors, you have to deal with a lot of timing diagrams. Those timing diagrams account for all of this. So if you're designing a circuit where you know that your rise time and your fall time are different, right? Like I just drew here, you would make sure that your timing would account for your clock time to account for both of them. So does anybody have any questions about this before we move on to circuit families? Okay. So the whole thing that everything we've built up to this point is we've been getting into these, basically a lot of this, and I think we're kind of 5.9, 5.10. I'll go up through 5.10 and then I'll dismiss because this question is pretty in depth. So we'll start next lecture with those. So 5.7 is this idea of ratioed logic. So everything we've come up to this point about skew and delays, that's all boils back down to understanding the ratio between the PMOS and the NMOS transistor sizes, right? Because all the way going back down to our doping and how we have to worry about capacitances because of the mobilities of holes and electrons. So everything boils back down to that. So all of this is kind of this notion of ratioed logic. So ratioed logic is any CMOS logic family where our output voltage is determined by the ratio of PMOS to NMOS. So we had our noise margins, and we have VOH and VOL, and then we have this VIH and VIL, right? And our whole goal was that our transitions needed to get somewhere in between there, correct? So what we're saying in 5.7 is this VOL specifically is related to beta P over beta N. So we have to reach some sort of output value of the voltage in order to be able to meet our threshold voltage for the transistors. In order to do that, creating our inversion region, and everything boils back down to this mobility of holes and electrons. So for 5.8, it's a resistive load is going to be a pull-up network. So we don't even have any inputs here. It's just RL, right? And we have a supply voltage that goes through some sort of resistive load. And we have 3 inputs that go into some pull-down network. So these are all NMOS. And so we have some sort of, we could actually calculate the resistivity of the pull-down network using our RC model. And our output voltage, low, is just that resistivity plus, divided by that resistivity plus our load resistance, and that's all multiplied by the supply voltage. So we have this asymmetrical response because when one of these are off, so if we have a 0 on one of these, then that cuts the whole thing off, and then it's just going to be a 1 automatically on the output. And so our delay, when it's going to high, so we've switched one of these to 0, which means we want this to go from a 0 to a 1 on the output. Our pull-down network is such that whatever combination is going to produce 0 to 1 on the output. So as a result, that's just going to mean 0. times 0.69, which I'm sure you recognize from circuits as the time delay model, right? RLCL, say your output capacitance, and then we have our parallel here, these two, which, as I'm sure you all know, is actually that. So low to high and high to low. All right. So let's go to the next family. So we're going to end at 5.10, and then I'll dismiss you guys. So this next one is a depletion load. So what we have here is we have our output is tied to the gate. So the gate and the drain of this PMOS transistor are tied together. So we have this depletion mode transistor is always on. We want to try to take advantage of this property to see if we can actually have this. So we have our inputs, right? So if we have some sort of input combination of our pull-down network that allows the flow to go to 0, right? Then the 0 is going to be here as well. So when Vin is 0, therefore the pull-down transistor is off, so V out is high. So what's going to happen is that we have our drain and our gate voltage as 0, and our source voltage is always 1. That just means it's going to consume a lot of energy. And then 5.10, and this is where we'll wrap up for the day. Pseudo NMOS. So here what we have is we have a PMOS transistor that's always tied to ground. So it's always on. So what ends up happening is we have to make the pull down network a specific size in order to account for that. So here we've stated we want to make the PMOS about 1/4 the effective strength of the pull down network. So we use our Elmore delay calculations using our RC calculations. We figure out what the resistivity of a pull down network is, and we make the resistivity of the pull up transistor, PMOS transistor here, 1/4 of that. And this is one that we're going to be using significantly more than the other ones for the rest of this section. Is known as pseudo NMOS. So the logic is driven by the NMOS, but it uses this PMOS transistor that's always on in order to drive it. So does anybody have any questions about that?
Where's the 1/4 come from?
The what?
Where's the
From calculation. Just from the fact that we have to deal with this actual ratio issue. So the whole goal is that they're trying to take advantage of the skewed to try to. The simple answer is that it comes from experiment. We could actually do a calculation, and I think in this next question here. It's a compromise between noise margin and speed. So through experiment. So just this diagram. And I'll start next lecture and go by going this into more detail. So for right now, it's just by experiment, and then we'll go into this table here, and then we'll go into a detailed. We actually kind of prove it. But for right now, it's just we experiment with the length to ratio. Here we have the logic voltages and static power consumption and delay. So it's a trade-off. So let me go back up here so those of you who are still copying 5.10. So if you have it copied, you're dismissed. Oh, I should note before you all leave, as you all are packing up, starting next week, I have a lot of travel that I'm going to be doing. I do go on conferences and all kinds of other stuff. So I'm going to be recording lectures. Both Monday and Wednesday next week, I'm going to be posting them online before. So you don't have to come in at 9 in the morning, which I'm sure makes you all happy. And then let's see. So let me look at it. So I know I got 28th and 30th. I'm going to be out of town, and then next Wednesday, the following Wednesday, the 6th, I will also not be here. Oh no, I think actually those two. I'm sure you will. Yeah, nothing was always more terrible than the professor's going to be out of town. I think I might actually both lectures of those 2 weeks. So trying to figure out what would be best. When's your next slate of exams coming up? Yeah, do me a favor. For Wednesday, I'm sure you all talk. Figure out when the next hunk of exams are, or the next big chunk of things, and I'll try to arrange the due date for the first project so that way it doesn't conflict with that. So let me know what that is and I'll make it work. All right, guys.